What we have here is a visualization of the Riemann Zeta function without the use of analytic continuation. It showcases the partial sums of the original Dirichlet series as the imaginary part t of its argument traverses the critical line. Now keep in mind that this visualization is truncated since we're within the critical strip, causing the zeta values to grow indefinitely. In the absence of actual zeros, it graphically depicts the continuous crossing of the origin of what might be perceived as the central point of the partial sums. As the visualization continues with larger values of t, it forms increasingly intricate patterns, all the while maintaining its trajectory across the origin. Now, the question that arises here is how to identify the center within a region where the zeta function doesn't naturally converge. Hello, and welcome to this video where we'll be taking a closer look at the zeros of the Riemann zeta function without relying on its analytic continuation. For those who might not be familiar with the Riemann zeta function, you can find excellent introductions right here on YouTube, and I've included a few recommendations in the video description. Zooming in a bit, within the critical strip, the divergence due to the zeta function's exponential and rotational properties reaches a point where it becomes harmonic, eventually forming an outward logarithmic spiral. Now, one way to locate the center involves using the spiral's growth factor. This method somewhat resembles analytic continuation, as it leads to a form of convergence towards a single final value. However, we're taking a different approach here. The reason is the idea that, as we approach the limit of convergence, valuable information about the function's evolution seems to vanish. This isn't how mathematicians generally perceive convergence. In fact, it's quite the opposite. Let's view the following typical perspective.
Functions. Now let me tell you a little bit more about the Riemann zeta function because that's going to be part of the story. So the Riemann zeta function is defined as a sum over the integers or a product over the primes, and these formulae work if x is greater than 1. But it turns out you can find formulae that match these.
In this fragment, you might easily miss it, but Professor John Keating argues that if sigma is smaller than or equal to 1, the zeta function not only fails to converge, but is basically non-functional. Strangely enough, the most intriguing region, where the zeros appear, is precisely the region where the function, to quote, doesn't work. Now, instead of going through the hassle of convergence, a more satisfactory workaround presents itself as we consider that repetitive summation or multiplication can often be achieved in a self-referential style. In this case, if the partial sums are harmonically divergent, we calculate them directly from the last two zeta terms without having to perform the entire summation. Let us refer to this as the self-localization of the zeta function. This concept of self-localization ensures that the unpredictable distribution of zeros along the critical line doesn't interfere with our analysis of their position on the critical line. These are, undoubtedly, two different things. Remarkably, self-localization based on self-referentiality doesn't require advanced methods in number theory. Basic geometry and trigonometry will suffice. Here's how it works. To begin with, the zeta terms evolve smoothly, forming a logarithmic spiral, which can be easily demonstrated through their complex exponentiation. In the case of the partial sums, such evolution isn't self-evident. However, if we examine the segments created by the individual terms and the partial sums, we can see that they share a common edge due to the complex addition. Furthermore, once the partial sums have begun to cycle continuously, each term, by definition, is positioned perpendicular to the original. This means that the number of increments per cycle must be the same for the terms and the sums, resulting in identical angles. So, for these segments to create cohesive spirals through scaling and rotation, it's essential that they form similar triangles. As all angles are uniform, the current zeta term must fall on the line connecting the next term with the partial sum. However, having the geometric alignment isn't enough. To pinpoint their positions accurately, we use the rule of cosine with those same zeta terms. I'm sure you see where this is heading. Let's first evaluate the complex terms. Now let's substitute these and combine the concept of similar triangles with the rule of cosine. What we've got here is the Zeta Orbital Equation, or ZOE for short. Now, this may seem somewhat complex, so the question is how to understand it and what you can do with it. First, it's important to note that the ZOE directly provides you with the modulus of the partial sum, assuming that the zeta function is self-localized. In other words, it represents a zero, although it isn't tailored to detect zeros. Instead, the ZOE's true strength lies in identifying an invariance with respect to t across all zeros. Let's take a closer look at what that means. To put the ZOE to practical use, we need to apply a form of dynamic truncation, which is typically most effective in conjunction with a specific value of sigma. As we're interested in the zeros, the most logical choice is truncation associated with the critical line. Research has shown that when the number of iterations is proportional to the imaginary part t squared, the ZOE value remains constant across all the zeros. In practical terms, this means we can simply replace t in the cosine term with the square root of n. Let's experiment a bit with the zeta argument s to observe its effects. We'll start with an arbitrary value for sigma and then shift t along that line. In this scenario, the ZOE value undergoes changes. However, when we set sigma to denote the critical line and increase t, the ZOE value rapidly converges to 1 and remains there. While the ZOE value, in a way, signifies a modulus, it effectively represents the zeta modulus for all the zeros. This means we have found an invariance that connects all the zeros to each other and to the critical line. Beyond the critical line, such an invariance doesn't exist. Let's illustrate the same graphically for an overall view. In this plot, our focus is on values of n that are extremely small in the context of the zeta function. Nevertheless, this scale offers valuable insights into the progression of individual ZOE terms and the overall ZOE value. Zooming out just slightly, all the plots practically blend with the Euclidean axis, rendering them virtually indistinguishable. This particular plot showcases a major zoom out along the x-axis, emphasizing the ZOE invariance when sigma is set to 0.5 and n equals t squared. The ZOE value is annotated as n increases. If sigma deviates even slightly from 0.5, meaning if s is situated outside the critical line, not only does the ZOE value fluctuate, but more crucially, its invariance with respect to t becomes compromised. The plot now shows how the ZOE evolves when varying sigma around the critical line. To sum it up, our analysis unveils an intriguing connection: self-localization of the zeta function, achieved without analytic continuation, is tied to an invariance rooted in the core properties of the function. Unlike the conventional zeros, this invariance consistently aligns with the critical line, hinting that Riemann's original insight was indeed correct. Ironically, while he established the context for his remarkable discovery through analytic continuation, it appears that this method did not secure the essential information required for the proof.